This is Geometry, Chapter 9, Section 5, Congruence Transformations. After our lesson today, you guys should be able to identify congruence transformations. And remember, congruence means that they have the same measure. And you should be able to prove triangle congruence using isometries. All right, so we're going to look at this problem, identifying equal measures. The composition, what does R mean again? It's like you're my mirror. My mirror's reflection. So R means reflection, and this is where the benefit of having notes is in your favor. If you don't remember what R stands for, flip back a couple sections and go, oh yeah, it's reflection. T means translation, thank you. And that's just moving coordinates, translation. So we're going to reflect and then translate and then reflect triangle ABCD. So that we get triangle XYZ. And then we're going to list all equal pairs and all equal side lengths. So compositions of isometries preserve angle measures. So we're going to get the same angle measures for each translation. So the measure of angle A is going to be the same measure as A prime. The measure of angle B is going to have the same angle measures of B prime, and C is going to have the same angle measure as C prime. Which translates to A goes with A prime goes with X, B goes with B prime goes with which one, X, Y, or Z? Y, and then C goes to C prime and C prime goes to Z. By definition, isometries preserve distance. So corresponding side lengths have equal measures. So side AB, let me clear our wackadoo picture. So side AB, right here, goes to which side on our XYZ triangle? Is it good? So we think it goes with XY. Side BC goes with which side on our XYZ triangle? YZ. And then that leaves just our last one here. AC, our hypotenuse, is going to go with XC. All right, so when we're looking at our key concept of congruent figures, two figures are congruent if and only if there is a sequence of one or more rigid motions that maps one figure to another. So as long as the motions are rigid and we're not changing the size or shape of our figure, then we're going to get two congruent figures. Okay, so we need to figure out, given this picture, which pairs of figures in the grid are congruent. For each pair, what is a sequence of rigid motions that map one figure to another? So one thing that I definitely see you guys do on your assignments is, instead of you say it looks congruent, that is not proof that it is congruent. Proof that it's congruent is showing that its length is 3, the other length is 3, they are therefore congruent. Just saying it because it looks like it does not make it congruent. So to map parallelogram ABCD to parallelogram HIJK, we need to have rigid motions. So we're going to move A, B, C, D a couple, let's see, we would have to move it 1, 2, 3, 4, 5, 6 units to the right, and 1, 2, 3, 4, 5 units down. And if you look, if I take this point B and I translate it to point I, I'm moving 6 units to the right and 5 units down. So if I look at our triangles, UVW, to get it to come over here and be Q and M, I need to reflect it across which axis? The X or the Y axis. So I'm trying to get this triangle to be this triangle. So I have to reflect it across which axis? So if I reflected it across the x-axis, it would come down here. Think about positioning. If I reflected it across the y-axis, it would come over here. V would be in the upper left corner. If I reflected across the x-axis, V would be in the same position as N, so it is going to be x-axis. Which is same as y equals 0. And then translated 6 units to the left. So we are going, reflecting it across the x-axis and then moving it 6 units left. Okay. So we're going to translate to the right 6 and down 5 of our triangle. So when you do a translation, it means your parallelograms are congruent. And then because we had a translation of down 6, or sorry, left 6 and over 0, and a reflection, then the triangles are also congruent. Because we had rigid motions both times. All right, so let's look at this problem number 3, identifying recording. What is a congruence transformation that maps NAV, so here's our NAV, to BCY? So what we're going to do is we're going to write the coordinates of each point first, and then see how we get from one to the other. Coordinate N is going to be at 1, 5. Coordinate A is going to be at 4, 3. And I always have to do this really slow because I have a tendency to mix these up. Coordinate B is going to be over 0, up 1. And you're going to put that here in your notes. And then our coordinates for our image are going to be coordinate B is at -4, -5. Coordinate C is at -1, -3. And coordinate Y is at -5, -1. So we're going to need to determine the rigid motion or sequence of rigid motion that maps triangle NAV onto triangle BCY. So we're going to look and see how each coordinate is related. First thing I notice, one set of coordinates is positive and the other set of coordinates is negative. So, but let's find a plan. Vertex N corresponds to vertex B. Vertex A corresponds to vertex C. Vertex V to y. So it appears that triangle NAB has been reflected across the x-axis and then translated 5 units to the left and no units down. So we have two rigid motion that happen. 2 rigid motions that happen. So when you look back at your notes, a reflection across the x-axis is when our x-coordinates stay the same and our y-coordinates are negative. So if we take coordinate 10, we are going to keep the x-coordinate the same and make the y-coordinate negative, just like here in the formula. And then we're going to translate it 5 units left. So I'm going to subtract 5 from 1. So then I get -4, -5, and that corresponds to vertex B. So we know vertex A is buddies with vertex C. And we're going to reflect across the x-axis, like we did for 11. And so we're going to take this A coordinate and we're going to make the 3, instead of 4, 3, we're going to go 4, -3. And then we're going to translate that 5 units to the left. So we're going to subtract 5 from 4. And we get -1, -3, which is our vertex C. All right, so we're going to follow that same process with our last vertex. So we can map B to Y. We're going to reflect it across the x-axis. We're going to take 0, 1, and we're going to make the 1 negative. And then we're going to subtract 5 from the x-coordinate. And we get -5, -1, which is y. So the congruence statement that maps triangle NAB to triangle BCY is first a reflection across the x-axis and a translation of -5, 0. All right, problem number 4, we're going to use the side postulate. We are given, and I always like to write down what we're given on our diagrams. We're given TD is congruent to EN, and YT is congruent to SE, and YD is congruent to SN. We need to prove that triangle YDT is congruent to triangle SNE. So step 1 is to rotate SNE about point S so that NE is parallel to its buddy DT. So here's where we did that. Oops. Here. So that's what we did here. We rotated it. So now they're the same rotation, so we can see, oh yeah, YD and SN and YT and SE and the hypotenuses are all congruent. Step 2, translate S and E so that points S and Y coincide. There it is there. So that would mean E coincides with T and N coincides with D. Underline the correct choice to complete your sentence. There is a congruence transformation that maps triangle SNE to triangle YDT. So we can say that the triangles are congruent And it verifies the side-side-side posture. And that's the end of our